Good evening, everybody. Thank you all for coming here today. I'm Devika, and I'm a program associate at Science Gallery Bengaluru. So today we have Parameswaran Ajit coming from International Center for Theoretical Sciences. Parameswaran Ajit is an astrophysicist at ICTS, Bengaluru. His research involves the study of universe using the observation of gravitational waves. As a member of the LIGO-Virgo team that made the discovery of gravitational waves, he is a recipient of a special breakthrough prize in fundamental physics and the Gruber Cosmology Prize. Recently, he was awarded the Tuoska's Young Scientist Award for Frontier Science by the World Academy of Sciences and was elected to the Fellowship of the Indian Academy of Sciences. Over to you, Ajit. Okay, thank you.
Okay, good afternoon. Thank you for coming today. I see there is some age difference in the audience. I will try to entertain the different age groups as much as possible, but yeah, we'll see how it goes. I will, black holes are, I assume most of you have heard of things called black holes. These are very fascinating and very enigmatic objects. And these ideas existed for a very, very long time. But in the last few decades, we have been studying them with closer and closer detail. And I will try to summarize this very interesting journey that happened primarily over the last 1 century. So that's the story of this. Okay, how is this one? Okay, so let's start with something. So if you throw a ball up, what would happen? It will come down, less like this, right? If you throw a ball up, it will come down. Why is it? Why does it come down? Yeah, it comes because the Earth has what they call a gravity. It tries to attract things. Even if you throw it, it will bring it back because it has a force of attraction called gravity, right? But somehow, this is something you have not tried. Suppose if you are able to try throwing a ball at very high speed, which is something like 11 kilometers per second, which is something that you cannot very easily imagine. What will happen is that this ball can go outside the Earth's gravitational attraction, gravitational field. This is called the escape velocity, right? And this is like a very high speed. For example, typically we walk at a speed of something like 4 kilometers per hour. Right? This is like even if we run, it's like 10 kilometers per hour. And you're talking about a 10 kilometers per second, which is like 3,600 times faster than that. Right? And typically our cars would go as fast as like 60 kilometers per hour or 100 kilometers per hour. I'm talking about kilometers per second here. Even the aeroplanes go as fast as like 700 kilometers per hour. This is extremely fast. So it's not very easy to throw a ball at this speed. But if you are able to do that, it can cross the gravitational attraction of the Earth and it will escape. That's what we call escape velocity. And it turns out that this 11 kilometers per second is not a magical number. It comes from a particular reason. It's only true for the Earth. Right? Basically, this is something that physicists can compute. You can compute. Basically, what you do is you balance the gravitational force to the force that you throw away. And if it turns out, this escape velocity is related to the mass of the Earth and the radius of the Earth in this particular way. These details of this equation is not very important, but you can see that this particularly related to this particular ratio of the mass and the radius. So, for example, the Earth was much more massive, then it turns out that the escape velocity would be very large. So this is something you might also have heard, right? If on the surface of the moon, you can jump very high because the moon's gravity is weaker, right? It's like 6 times weaker. So that's why you're able to jump very high. And it's consequently, if you are going to some even heavier object, like for example, the sun doesn't have a surface, unfortunately, but if there is a surface, if you try to throw a ball from the sun, and if you want it to be escaped, this escape velocity is like 600 kilometers per second. It's much more than that. The reason is that the sun is something like 1,000,000 times more massive than the Earth, but it's only like 100 times more, the radius, the size is only 100 times bigger. So it's much more dense, it's much more compact on average. That's why the escape velocity is very large, because this m by r is very large. The compactness is very large for the sun. You can now imagine again, there are some very interesting stars called white dwarfs. So the sun would become a white dwarf after a few billion years. It's very, very far later. Basically, those white dwarfs are basically some end states of normal stars like the sun, because once they exhaust its fuel, it will contract because of the force of gravity and become a star called the white dwarf. And white dwarfs, there are a few different kinds of white dwarf, but there are the so-called carbon-oxygen white dwarfs. They have the interior is like a crystalline structure. It could be like diamonds, for example. So, and these, a white dwarf is as massive as the sun, but it's only as big as the Earth. So imagine compressing this big sun, which is like 100 times bigger in size as compared to the Earth, and 1,000,000 times more massive, and compressing it to the size of the Earth. Then it's an extremely dense, an extremely compact object. And here, the escape velocity is 5,000 kilometers per second, much more than that, because you are creating a much more dense object. Now you can play this game. Suppose you are making this object even more dense, right? Compress it even further, like 3 kilometers, something like that. This escape velocity will continue to increase, and eventually it can reach something like 300,000 kilometers per second. And then it means that you are able to throw a ball outside this object only if you are able to throw it at this velocity of about 3 lakh kilometers per second. But now there is a problem. It turns out that this is the velocity of light. This is the speed of light travels. And it turns out that nothing can travel faster than light. I will tell you a little bit about that a bit later. So this means that even if you basically shine a laser beam from the surface of this object, it won't be able to escape. It will just come back, because the escape velocity is so high. And basically nothing could escape this extremely compact object. And this is, you could think of this as a black hole. And so far, all this argument is purely using Newtonian physics, which, if most of you have studied in school. And, Newton's theory of gravity was around for the last 400 years. So the last few centuries, people have been speculating about objects like these things, these dark objects. So this person called Pierre-Simon Laplace. He's a very influential French mathematician and physicist, lived in this time. So he basically speculated that it is therefore possible that the greatest luminous bodies in the universe are on this account invisible. The most massive object that might exist in the universe might be invisible to us because light is unable to escape these extremely luminous objects. So people have speculated this. There's another person called John Mitchell. He's an English clergyman. In fact, he's a priest in the Protestant church. And he also speculated another interesting possible way of observing such things. Laplace said, it means that these most massive objects could be invisible. But he also said, if other luminous bodies should happen to revolve around them, we might, from the motion of these revolving bodies, infer the existence of the central lines. It's very complicated English at that time. But essentially it means that even though you are unable to see these dark objects, if you have another object, like a star, that is moving around it, from the fact that we are seeing some object circling around some dark object, we might be able to infer the presence of these dark objects. And it turns out that these two things are very prophetic. It turns out that the most massive objects that we know in the universe are these dark objects called black holes. And in fact, the first means of detecting these objects are by looking at the motion of stars or other objects around these dark objects. That's how people have discovered black holes for the first time. So now let's change gears a little bit. This was so far a very, this is not a case. So far what I have told is not true. This is not the right description of a black hole. Because it turns out, as you said, the light has no mass. So you cannot ask about this question about throwing the balls, etc. But basically the same effect survives for different reasons. And this is, again, calculated very carefully by Albert Einstein and many others who looked at this theory of gravity called the general theory of relativity. It turns out that the most accurate theory of gravity that we have right now is not Newton's theory of gravity, but it is due to Einstein, and it's called the general theory of relativity. And it provides a kind of different picture of gravity. So according to Newton's theory, basically gravity is a force, right? Any massive object will attract each other through a force of gravity. And for example, my two hands are even attracting each other, but because it's too weak as compared to the gravity of the Earth, I'm not feeling it. But if you go to space, and if you have two free floating objects, they basically would move because of the presence of the companion. And the fact that the Earth is orbiting around the Sun is because of the gravity between the Earth and the Sun. And according to Newton, it's a force that is acting instantaneously on the other objects. If you produce we see the gravitational force of the Sun right now instantaneously. But it turns out that it is in conflict with this other very important observational fact that nothing can travel faster than light. And basically, Einstein's theory circumvents this problem by coming with a totally different description of gravity. And it turns out that gravity is not a force, but it is a manifestation of the curvature of space and time. So any massive object, like an apple, would curve the space around it. It also makes the time run slower. And that's what the curvature of time means. And it's something very hard to imagine, but one could actually do experiments to measure these things. So in the absence of any massive objects, for example, very, very far away from free space, where there is no massive object around it, basically our space is flat and time runs at certain speed, and so space-time is flat. And you can measure this flatness of space-time by just drawing a triangle. If you draw a triangle and add the angles inside the triangle, it will add up to 180 degrees. It's again something that we learn in school, in Euclid's axiom. But it turns out that if you do the same thing in the vicinity of a very massive object, these angles won't add up to 180 degrees. This is something that we actually see in real life objects also. If you take a football and draw a triangle on that, you would see that these angles would add up to a number greater than 180 degrees because the space is curved. So basically, Einstein's theory says that massive objects curve the space-time around it, and very, very far away from any gravitating object, the space-time is flat. This is something very abstract and something we cannot imagine it, but one can calculate things, and it makes very solid experimental predictions, and astronomers or laboratory experimenters can go and measure these things. So again, this is the last equation that I will be showing. Basically, Einstein summarizes his key idea in this equation, which is called Einstein's equation. It makes sense, made by Einstein. And basically, the left part of this equation is a quantity that describes the curvature of space-time. And the right part basically contains whatever matter contribution in the space, like mass, energy, angular momentum, etc., that is contained in the space-time. So basically, it tells you that the amount of space-time, amount of matter in any given place will tell you how the space-time is curved. And because of the space-time is curved, the matter moves in a particular way. So this is very summarized by it's very interesting quote by this American physicist called John Wheeler. He says, the space-time tells matter how to move, matter tells space-time how to curve. What does it mean? Basically, the Earth is moving around the sun because of the space-time curvature produced by the mass of the sun. And because there is the sun and the Earth, their present mass is actually curving the space-time. So they are basically coupled back to each other. And so this is the summary of the Einstein's theory of general relativity. And basically, the core of this theory is this set of equations called Einstein's equations. And Einstein thought that, oh, this is a very interesting equation, but he didn't really think that there would be a lot of consequence to this in terms of real objects. And this person, called Karl Schwarzschild, he was a German astronomer, physicist, very talented person, unfortunately died very young. He, within a few months after Einstein's published his theory of general relativity, he found a mathematical solution to this Einstein's equations, which basically describes the space-time curvature or the gravitational field caused by a spherically symmetric object. So this is again a cartoon of how the space-time would look like around a spherically symmetric object. And it's something that, a space-time has 4 dimensions, the space has 3 dimensions, and time has an extra dimension, so you cannot imagine it. So these are some simple 2-dimensional representations of how one could imagine the curved space-time would look like. So basically, if it was an object like this was the only object in the universe, the space-time would curve like this, like this funnel. And later, when people looked at these particular mathematical solutions, they found very interesting properties. These mathematical solutions contain some very interesting properties. One is that if a given mass is enclosed in a particular radius, if you are able to compress the mass to a small enough radius, which is called the Schwarzschild radius now, it turns out that not even light can escape from that. So we are coming back to what we kind of found from this simple intuition by compressing things and calculating the escape velocities. If you are able to compress the mass into a radius, which is a given radius called Schwarzschild radius, it depends on the mass, then it forms a very strange surface around it. It's called the horizon. And it has a very interesting property. It's like a one-way street. Things can go inside, but nothing can come outside. Even light cannot come outside. And more interestingly, or more strangely, at the center, we don't know what is happening. At this center, there is we call it singularity. All our physical laws that we know today breaks down, and we don't know how to describe physics at this point. It's called singularity. So basically, whatever that falls inside, it could be light or planets or TV sets or people. If you throw them inside, they would all fall into this central singularity, and we don't know what would happen to them. So nothing would come outside. And for example, this particular radius for an object as massive as the sun, it's about 3 kilometers. So for example, if you're able to compress the sun, which is a radius of about 100,000 kilometers, if you compress it to a radius of 3 kilometers, it will form a black hole. And how do we think of it? We cannot think of light in terms of this escape velocity, etc. The modern way of thinking about it, at least one way of understanding it, is the following. For the light to go out of this gravitational field, the gravitational potential, it has to do some work. Yet it has to climb up this gravitational potential. And by doing that, it loses its energy. And it loses its energy means it goes to lower and lower frequencies or higher and higher wavelengths. This is called the gravitational redshift. So here, for example, suppose there is a disk of gas here, which is very hot. It is emitting some, let's say, X-rays, for example. As it climbs the potential well, these X-rays will go to longer and longer wavelength, to visible light, radio waves, etc. But eventually, if you are sufficiently deep inside, this wavelength is so large that essentially you just appear dark. We won't be able to observe it. So if this object was at the horizon, we won't be able to see light rays coming from that. So basically, that's why the black holes are dark. So can black holes exist in the, so far, this is just a mathematical idea, right? There is this set of equations, and there is a mathematical solution to that. This mathematical solution has this particularly interesting property. But do these objects exist in the universe? Can these objects exist in the universe? The first thing. So it turns out that there is a way possibly such objects could exist in the universe. And that's the way the following. So in a star like the sun, how does the sun shine? Do you know? There has to be some fire that is lighting up in the sun, right? It turns out that the sun is powered by nuclear reactions happening at inside. It's a nuclear fusion reaction. And these lighter nuclei would combine to form heavier nuclei, et cetera, and that's how it burns. But eventually the sun will run out of its nuclear fuel and it will get dark. And what would happen is that then the gravity which is trying to compress the sun would win. The sun would collapse. Now usually, right now it's some sort of a balance. Gravity is trying to compress the sun. However, the heat as well as the pressure of the light itself has a pressure. It's called radiation pressure. It is trying to push the sun outside. So there are these two opposite forces that are in equilibrium, and that's called hydrostatic equilibrium. That's how we see the stars right now. But once the nuclear fuel gets exhausted, there is no pressure to pull it outside, and the gravity wins, and it collapses. So it can collapse to, if nothing is there to arrest the collapse, it can collapse to a black hole. It's quite possible. And it turns out that, so these two people, first Oppenheimer, who is very famous now because of the movie, and his graduate student, Karl Schwarzschild, so they were the first one to show mathematically that when all thermonuclear sources of energy are exhausted, a sufficiently heavy star would collapse and form a black hole. And I have this interesting question mark picture. There is this person, very interesting. So this was published in 1930 or something. And it turns out there was another paper by a very enigmatic person called B. Dutt, who lived in Calcutta, who published a similar result a year before. Of course, this calculation was a very mathematical calculation, which really did not discuss the profound physical implication of such a calculation, that unlike Oppenheimer and Snyder. But it turns out that there was someone who has thought of this collapse and who published a paper a year before Oppenheimer and Snyder. And this person remained enigmatic until 5-6 years ago. We had no information of who this person was. But now we have some information. So it turns out this B. Dutt was a student of a very famous Indian relativist called N.R. Sen, who lived in Kolkata. And unfortunately, he died very young because of an operation that went wrong. So he died maybe a year or two, a few years after he published this paper. So unfortunately, we don't have a lot of understanding of what this person was, and we don't even have a picture of this person. So okay, even this one, there is a star. There is some like a fine print here. So they made certain assumptions for this to happen. They assume that the stars are exactly spherically symmetric. They are exactly like spherical balls. But there were a lot of questions. For example, we know that in the universe there is nothing spherically symmetric. So even if you take a ball, you can approximate as a spherically symmetric object. But if you look at it with a closer eye, with a microscope, you see, roughness on the surface. It's not exactly spherically symmetric object. If you take a star, it's broadly spherically symmetric, but it has convection layers. It has things going up and down. It is not a spherically symmetric object. So nothing in the universe is actually spherically symmetric object except a black hole, in fact. So the question was, is it this calculation that Oppenheimer and Snyder did, is it valid for the real objects in the universe? And later in the 1960s, Roger Penrose, using very, very sophisticated mathematical techniques that is beyond the capability of me and most of the people in the room. He showed that under a very reasonable set of general assumptions, this is true. A sufficiently massive star would collapse. So black holes can exist in the universe. And it's a very robust kind of calculation. And he was also awarded the Nobel Prize year or two before last year. But now, whether can black holes exist in the universe and do black holes exist in the universe are two different questions. So far, the theorists, mathematicians and theoretical physicists have shown that black holes could exist in the universe. But in the same time, astronomers have started finding very interesting objects using radio observations in the 1960s, which possibly hinted to the existence of black holes in the universe. And these are radio observations of some very, very bright jets of gas, very hot gas. So this is some source of a very powerful jet. It's going like megaparsecs, like millions of light years. The size of these jets are like millions of light years. It's huge, And in the 1960s, astronomers discovered several such extremely luminous objects. And people try to understand what is powering these extremely luminous objects. Could this be nuclear fusion? Could this be fire? Could it be nuclear fusion? It turns out that even nuclear fusion, which is the most energetic process that we knew, they could not produce this kind of energies. And the only thing that would fit the bill is that it could be powered by gas that is falling into some supermassive black hole and losing because of its infall, it heats up. It is basically losing up this, changing the potential energy in the form of this very hot light. So the gravitational potential energy released by infalling matter to supermassive black holes that are a million times more massive than the sun, it seems to be the only possible explanation of these extremely energetic jets that we see. So Laplace turns out to be true. It is possible. Laplace speculated 200 years before that the most luminous bodies in the universe are on account of this invisible. No, it is, again, the black hole is invisible, but we see its effect on this. And these are some of the most luminous objects we see, like quasars, active galactic nuclei, et cetera, et cetera. There are also other ways of, other observational evidence also came for this. This came from X-ray astronomy. This is, for example, this is an X-ray image of this very bright object called Cygnus X1. It's using an X-ray telescope to look at the sky and use this image. And again, it turns out that this is actually produced by a binary system involving one black hole and one normal star. So if a normal star is moving around the sun, this black hole, sorry, and basically this normal star is very big as compared to the black hole. It's very tiny, but it's very, very massive. So it's very compact. And because of this large density gravitational gradient, this black hole, this star is losing its gas to the black hole. Basically, the gas is falling into this black hole, and this process is called accretion. So basically, this infalling matter onto this black hole is producing a disk of very hot gas, which basically emits X-rays, and that's what we see as this one. And how do we know that it's a black hole? Because of this motion of this star around the black hole, it has an imprint on the observed spectrum. It's called Doppler shift, something that is causing this particular change in the pitch of the whistle of the train when it comes through you and goes away from you, right? It goes like to and then so on. So this is called a Doppler shift, and from that you can measure the mass of the sun, of this unseen object. We don't see the black hole. It turns out to be like tenths of solar masses. So there's a dark, massive object, and the only thing that we know of is a black hole. So there are, again, this is something that, and these are not very rare objects. It turns out that there are like 10 million such objects in our own galaxy itself. So astronomers estimate that there are something like 10 million such black holes in our own galaxy. And our galaxy is just only one galaxy among about 100 billion galaxies in the universe. So the black holes are ubiquitous. But again, remarkable that something like John Mitchell said, right? The motion of luminous objects around these dark objects could provide hints of these existences. Precisely that's what the astronomers do. They basically move the to measure the motion of these objects around these black holes to infer the presence of these dark objects, which is called the black hole. Now, in the last few decades, we have been photographing black holes to closer and closer detail. And how do we do that? And that has to do with how things move around black holes. So black holes have some lot of enigma, and it also generates some amount of panic among people. And they are supposed to devour everything around it, etc. But it turns out that if you are sufficiently away from a black hole is as harmless as any planet or a sun, etc. So for example, this is the orbit of planets in the solar system, right? Suppose you were to replace the sun with a black hole of the same mass, nothing would happen to the orbits of the planets. They would go in the same way. Of course, we would not have any light and life, etc., etc. But as far as the orbital motion is concerned, there's no problem. So a black hole very far away from a planet is very harmless. It doesn't do anything, except it does the same gravitational thing as the sun would do. And just like we are able to measure the mass of the sun from the motion of planets, we can also measure the mass of the black hole from the motion of the planets around or stars around it. Have you ever thought of how we measure the mass of the sun? We know fairly precisely how much the sun weighs. The sun has a weight of about 10 to the power 30 kilograms. Have you ever thought of how does one measure the mass of the sun? We can't put the sun on a scale, right? It turns out that from Newtonian gravity, from the speed of the planets around the sun and its distance, we can measure the mass of the sun. So if you have the orbital period as well as separation from the sun and the planet, we can measure the mass of the sun using Newton's equations, Newton's laws. And this is called Kepler's laws also. And the same way, it turns out the astronomers have been actually observing. Okay, I have a video which I would like to play here. So this is, astronomers have, we are living in this galaxy called the Milky Way, right? We all know. And the Milky Way has a center, believe it or not. And we know it's in a constellation called Sagittarius. And this is something that astronomers knew for the last couple of centuries. And it turns out that there are a bunch of stars orbiting around something dark in the center of the galaxy. And this movie that I'll show is not an animation. It's actually made by combining a large number of very sophisticated astronomical observations using the biggest telescopes in the world over a period of about 20 years. This is like 1995. You can see that. It goes up like 2010 or something. So each of these little blobs is a star. And I will play the video, and you can watch how these stars move. So it goes up to 2019, right? So it's like really 25 years of observation. So you can see, okay, now it's going to something else. Okay, let me just bring back. So basically, these black holes, these stars are moving around some dark object. They have not completed, many of them have not completed their full orbit, but some of them have. For example, this one has, etc. And just like we are able to measure the mass of the sun from the orbits of planets, we are able to measure this mass of the central unseen object from the motion of these stars. And it turns out that this object that we cannot see, which is shown by this white star, it's a marker. This object has a mass of about 4 million solar masses, 4 million times the mass of the sun. So remember, the sun itself is like 1,000,000 times more massive than the Earth, and this central object is 1,000,000 times more massive than the sun. So these objects are moving around a dark, million solar mass object, and we think this is a supermassive black hole sitting at the center of the galaxy. And these two people, Reinhard Genzel and Andrea Ghez, led two teams of astronomers, one in Europe and one in the USA, who made these very painstaking observations for the last few decades and established that there is actually a supermassive compact object at the center of a galaxy. We think it's a supermassive black hole. And they received the Nobel Prize again, along with Roger Penrose a couple of years ago. And okay, now this is again one way of measuring a black hole. And the last decade, we have been trying to look at these black holes at closer detail. And this has to do with what is happening at very close vicinity of black holes. So far we have been observing these stars, which are fairly far away, orbiting these black holes. But if you are very close to this black hole, like a few Schwarzschild radius away, it turns out that more interesting things would happen. So for example, it turns out that if you go to some orbit that is closer to 3 times the Schwarzschild radius, no object can circle around the black hole. It would invariably fall inside. There is no stable orbit. And more interestingly, if you go to about 1.5 times the Schwarzschild radius, not even light can orbit. Okay, there is an interesting orbit called exactly at 1.5 Schwarzschild radius. If you put a light ray there, this light ray would continue to circle the black hole, would never escape. But if you just give a small perturbation, it will either fall inside or go outside. This is called a light ring or photon sphere. So basically, we were seeing these large stellar orbits. These are these S2, these different stars that we have seen earlier. But if you go to zoom into the central and zoom in, and very close to black hole, there is very interesting surfaces called last stable orbit and the light ring, etc. And astronomers, radio astronomers, have been trying to see what exactly is happening at this close to the center of the black hole. And this is basically an image made by a number of radio telescopes happening at, located at different parts of the globe. And they combine their data to produce some sort of a synthetic radio telescope that is as big as the Earth. This is called the Event Horizon Telescope. And using this extremely big synthetic telescope, they are able to construct an image of this galactic center object. And they see this very strange kind of ring with a black shadow inside. And we think what we are seeing is a shadow of the supermassive black hole, just like this. So we are now seeing these, it's like a close-up photograph of the black hole, while the star orbits will give you some sort of a wide-angle view. Now, how do we know that this is indeed a black hole? It requires a certain amount of theoretical calculation. So what astronomers do, or theorists do, is basically solve these Einstein's equations for a black hole with a lot of infalling gas and compute what kind of image they would see. And it turns out that if you put a black hole, you would see something like this. And if you put some other object, not a black hole, but some other kind of strange kind of objects, you can see different kind of shapes. And you compare the observed photograph with this kind of synthetic photographs to get a guess, to infer what is the true nature of these objects. And the most likely what we are seeing is a supermassive black hole as mathematically discovered by Schwarzschild. But again, it's not entirely clear. This could be something more exotic than a black hole also. And again, scientists have a lot of imagination. They are coming up with more exotic objects also. So we need more data to tell apart whether this is indeed a black hole or something more exotic objects. And astronomers have been helped by a new messenger in the last decade. And this is something I personally work on. I'm very interested in this. This is observation of gravitational waves. So far, all the observations I've been talking about was using the observation of light, radio waves, X-rays, optical light, etc. But gravitational waves are totally different. They are basically ripples in space-time curvature itself produced by the motion of these massive objects such as black holes. And here is a theoretical calculation. It's a numerical simulation, and it's showing the kind of ripples that we would see when two black holes orbit each other, emitting gravitational waves. And because they emit gravitational waves, they would come closer and closer and eventually collide. And let me show you this video. And okay, so this is so you have these two black dots. These are the black holes. And what you see in the background is a representation of the space-time curvature produced by these black holes. And they are orbiting each other, and they are emitting gravitational waves, as shown by this one. This is observed gravitational waves. And they come closer and closer, and hence they emit more and more gravitational waves. And because of that, they would come closer and closer faster. They would in-spiral faster. And eventually, these black holes would collide. They would merge. This is the artificial freezing of this time, just to see what is happening. The simulation is free. The video is frozen for some time to see what is happening. The speed is reduced. But okay, now they merged to form a common horizon, and they finally form this black hole. And you would see this. Now this animation would, the camera would pan out and see these ripples produced by these objects. And this is called gravitational waves. And in the past decade, since 2015, in the last 8 years or so, we have been observing these gravitational wave signals produced by colliding black holes using these two remarkable observatories called LIGO, one is in the USA, and Virgo in US. And there are ongoing plans of building one detector in India, also called LIGO India. So we have so far observed about 200 different gravitational wave signals produced by colliding black holes at different parts of the universe. And one nice thing about gravitational waves is that they contain very detailed nature of this object that is producing these signals. So remember, black holes themselves cannot produce any light, right? So whatever observation that we are seeing were the light produced by gas in falling to the matter or objects orbiting the black hole, etc. They are indirect observations. While the gravitational waves are produced by the motion, the disturbance in the space-time curvature produced by the motion of the black hole. So they contain much more details of the intrinsic properties of the objects. So in the next decades, we will be able to tell whether what we are seeing are indeed black holes or something more exotic. So it's a very exciting time to study black holes by combining all these different kinds of observations and theoretical studies. So let me summarize. What do we know so far about black holes? So from theory, we know the following things. So Einstein's theory predicts the existence of black holes. And what are black holes? There's a singularity that is covered by what is called a horizon, which is like a one-way street. And they can be formed through the collapse of massive stars. We have a pretty good understanding of how they could collapse. And more interestingly, I told you that there are no spherically symmetric objects in the universe, except possibly black holes. It turns out that while these black holes are very enigmatic and exotic, they are also the simplest macroscopic objects in the universe. A black hole has only three properties. It has a mass, it has an angular momentum, it has an electric charge. If you tell these three properties, you can compute everything about a black hole. And that's very difficult for any object. If you want to describe this object, how many parameters do you need? Right? You need to it has a shape, very complicated shape. It has a color. It has a particular density. It has a particular material properties. So you need so many parameters to describe even a simple object. But it turns out that black holes can be described by just three properties. And if you prescribe these properties, you can compute everything about them. So this means, essentially, it goes by saying that the black hole has no hair. It's called no hair theorem for black hole. And this is a cartoon made by a very famous black hole physicist called C.V. Vishweshwara, who is from Bangalore, who is a founder of the Jawaharlal Planetarium, who was a professor at Raman Institute and IIA. And it's, for people who know this Occam's razor joke, you can see this Occam is shaving the hair of the black hole. to making it. It has, so if you look carefully, it has 3 hair. There's no hair. And one hair is a mass, one hair is electric charge, one is angular momentum. But all these are, I was talking about in terms of classical physics. I have not considered the quantum effects of black holes. It turns out that if you include the quantum effects of black holes, it has some very interesting, strange properties. For example, some amount of radiation can come out of this black hole called, for example, Hawking radiation. So my colleague Subrat Raju was supposed to give this talk. I'm just stepping in for him. If he was giving this talk, he would have talked a lot about the quantum effects of black holes and much more exotic phenomena that you would see in the black holes. Finally, what we know in terms of observations. So we have several lines of compelling observations that black holes, or objects that are very, very much like black holes should exist in the universe. So there are 3 broad classes of black holes. One are called stellar mass black hole. Their masses are comparable to stars, a few times the mass of the sun to a few hundred times the mass of the sun. Some black holes are supermassive. They have millions to billions of times the mass of the sun. And it turns out that most galaxies that we know have supermassive black holes at their center. There is a third class called intermediate mass black holes, which has mass about 100 to 1,000 solar masses. We don't know they exist or not. There is some debate going on. It is not clear how supermassive black holes are produced. So for example, we have a pretty good understanding of how these stellar mass black holes are produced. They are produced by the collapse of massive stars. But we do see these supermassive black holes that are billions of times more massive than the sun. We have no clue as to how nature is producing them. There are many theoretical ideas, but it's not clear which one is actually working. We are starting to test some of the very fundamental predictions of the nature of black holes. For example, do they have a light ring? Do they have a horizon, et cetera, et cetera? But what we don't know yet is that are these massive compact objects that we see through various observations, are they black holes as predicted by Schwarzschild, or something more exotic? Again, we don't know. Okay. So, and this hopefully will be answered by observations, astronomical observations, and theoretical work in the next few decades. So it's a very exciting time to study black holes, because all these fronts, observational fronts using electromagnetic waves and gravitational waves, theoretical calculations using analytical tools as well as supercomputers, all they are coming together to help to aid the study of black holes. So let me stop here, and thank you very much.